important source of performance. We have some excellent speakers here that we hope you will find to be synergistic and looking at the material science and the mechanistics between these aspects. So if we go to the next slide. So our first speaker is Craig Perkins. He joined NREL in the year 2000, and he's now a senior scientist there. I'll let you read this. These slides will be available after the talk, and I think we'll both post them and send them. We also have Clemens Ilse from the Fraunhofer Institute, where he works as a researcher at the Center for Silicon Photovoltaics in Halle, Germany, and also at the Anhalt University of Applied Sciences. So with the next slide. So our opening announcements here, I wanted to take only 4 or 5 minutes here. We'll have our presentation by Dr. Perkins and then Clemens Ilse, and then we'll take questions, but please do that through the little bubble that you see here on the right-hand side. It says chat. If you scroll over it, put your questions there, and one of us will moderate that and ask the questions. So with that, I'd like to introduce Dr. Craig Perkins and transfer the slides control to him.
Okay, thank you very much, Greg. Again, my name is Craig Perkins. I'd like to tell you a little bit about some work that we've been doing over the last year or so to understand adhesion and in particular particle cementation as it applies to PV module soiling. I thought cementation would be a particularly interesting topic for this webinar, and for a number of reasons, one of which is simply that as a community, I believe that we have not really adopted a good and testable definition of what we mean by cementation. And I would argue that if you can't define something, then you're probably not really studying it. As a more practical matter, as individuals, I think we open ourselves up to criticism, whether it's on a manuscript or a funding proposal, that if we can't define what we're trying to study. Fortunately for us, for a number of years, the cement industry, not surprisingly, has had a fairly rigorous definition of what they mean by cementation. It turns out that cementation is a phase transition. It's an example of what's known as a percolation transition. These are characterized by random formation of bonds between ensembles of particles. Now, the particles can be atoms, polymer molecules, or in this case, we're talking about dust particles. This can happen in 1 or 2 or 3 dimensions, and this graph, this figure here, just shows the formation, a fraction of a total number of bonds that can form in this little 3-dimensional array of particles. Now, if you look at this, it's not immediately obvious, to me anyways, whether or not this is something that you can say, give a thumbs up or thumbs down to, whether or not we've transformed this agglomeration of unbound particles into something that is a monolithic solid. This was an early question that came up by one of my colleagues here at NREL, and it turns out that's a super interesting question, and there's actually an ongoing vigorous academic debate of whether or not percolation transitions in general are continuous or abrupt. And if you're interested in the nitty-gritty of this, I can refer you to this science paper from 2009. For our purposes, though, I think this doesn't matter so much, but in practice there is a qualitative and discrete difference between cemented and uncemented particles, whether they're in 3 dimensions or a thin film of the sort that is of interest to the PV community. and that is that cemented particles transmit shear forces and shear waves, whereas uncemented particles do not. So this there's a schematic on the left-hand side here showing an experimental setup that's used by people. There's a small group of people who are both experts in ultrasonics and acoustical properties and the physics and chemistry of curing cements. And there's the figure on the right shows essentially sound velocity, shear wave sound velocity in a whole bunch of different types of cements as they have cured. So the x-axis on that graph on the right is simply time after the slurry has been mixed together. That's from the ultrasonics paper from '93. And if you pick any one of these curves here, you'll see that at low curing times, the sound velocity has dropped to 0. Essentially, it's not defined. The shear waves are not propagating in this wet slurry. And then at some point, there's a well-defined shear modulus that allows the shear waves to be to propagate through the material. And this is actually used heavily in the cement industry and in cement research to understand how different additives affect and different processes affect cement curing. Well, that's great for you know, say a bucket of cement, but how do we apply this to 2 dimensions or thin films that are, again, more of interest to the PV community? Well, the answer to that is actually sitting in probably many of our laboratories, and that is quartz crystal microvalves, which are shear wave resonators. We have a number of these devices in our lab and have used them for years, but at the beginning of this project I realized this is probably something we could use to study adhesion and cementation. So that on the left there is just a picture of a 1-inch MaxTech resonator. This is coated with SiO2. All the data that I'll show this afternoon or this morning is on SiO2 coated resonators, so to mimic the glass that we would find in a typical PV module. This type of equipment usually measures frequency and frequency changes, which is shown on the left of the graph on the right, but also crystal resistance. That's something that maybe is less commonly used by people who are using PCMs just to measure thicknesses of films, for example. But for our purposes, the resistance is a very useful output for this instrument because it's proportional to the shear wave damping in non-rigid layers. This graph is one of the very first sets of data that I took with the instrument, and it's a relatively crude experiment. I simply dipped a Q-tip into a bucket of Arizona road dust that was sitting in our cabinet. This is a standard material that you can buy from a number of different vendors, and then just flicked it onto the surface of the crystal. So what you see there after 2 minutes or so is what you kind of would expect, at least in a fairly naive interpretation. We see a decrease in the crystal frequency, and if you make a number of assumptions, you can convert that directly into mass per unit area. Excuse me. But also you see that the crystal resistance increases dramatically. Now, if this had been a thin film of some sort that was rigidly adhered, you would see no change in resistance. So right away we know that this initial application of Arizona road dust is characterized by tightly bound material that causes the change in the drop in the frequency, because simply we've added mass to the resonator. The resonant frequency has decreased, but then essentially losses, acoustical losses, are occurring at the same time. So that means there's some loosely bound material. Another interesting aspect of this experiment was that it's a self-limiting process. So with increasing doses of dust, you see less and less response. And in fact, on the third application, only the third application, there's very little change and no discernible change actually in the frequency, although there is a small change in the crystal resistance. And then finally, I just used a duster, a little portable air duct, to remove the dust, and it turns out that you see the crystal resistance drop all the way down to where it was initially, but the frequency doesn't return to its origin, which means we're left only with very tightly bound dust. So this to me was really interesting and showed that there's a number of things we could get out of experiments using this quartz crystal oscillator. Let me go back to this slide here. There's a couple things about this that I did not understand though, and if you look after the first dust application, you can see there's a fairly long change in the frequency, and actually in all cases that it seems to be moving around with time. Now these instruments are normally super stable. This Arizona road dust is fairly complex in terms of its particle size. There's a fairly broad distribution of particles. There's a number of different minerals involved in it. So there was a motivation to try to understand things on a little bit more fundamental basis. Our analytical microscopy guys, who we've heard, I think, have presented to this group before, have been doing a number of AFM experiments and trying to quantitatively understand things like capillary forces and van der Waals forces. In those experiments, the probe are SiO2 spheres of about 20 microns. So I obtained some of these spheres. In this case, they're 50 microns, and I did the same sort of application to the resonator and immediately opened up a can of worms. And I modify that with the word fortuitous because although it did initially baffle me, we ended up learning quite a bit about the interactions of particles and quartz crystal resonators. There's two things about these results that were initially very puzzling, and that is that when we put the soda glass spheres on top of our resonator, we see a positive change in the frequency. It's as if the quartz crystal got lighter, as if it lost mass, which I did not understand. The other thing that was puzzling to me was a fairly large drift over time, which also was puzzling to me. But then again, this is something that we saw with the Arizona road dust. Thanks to our wonderful World Wide Web of information, I almost immediately came across a paper that explained this, and it's interesting to me that this is a fairly recent paper. I mean, it's from 2010. I would have thought that, decades ago someone would have figured this out, but it's a relatively recent result. So it turns out that you have typical QCM behavior, and when I say typical, I mean that you put particles on something and the frequency decreases only if the resonant frequency omega s of the particle itself is much larger than the resonant frequency omega of the resonator. So that's the case for molecules or very rigidly bound films. If you have large particles, in this case glass spheres that are larger than about 40 microns, then what happens is inertia clamps the particles in place while this resonator moves underneath it, and the particles essentially exert a restoring force on the crystal, which effectively increases the stiffness of the resonator. So you end up having a positive frequency shift. So rather than the mass sticking with, oscillating in frequency with the in phase with the crystal, it just stays in place in space. And we expect to see positive frequency shifts. So there's a nice paper by a guy, Joe Hansman, who over years has done this, looked at glass spheres and figured out some really interesting ways to use QCMs to understand friction coefficients of well-defined particles. So that explains qualitatively the sign of the frequency shift, but it doesn't explain the shift with time. And again, people have figured out why these friction coefficients change over time, and this is due to a phenomenon called capillary aging. And this involves essentially the spring constant between those particles and the friction coefficient depending on the contact time. This is a really interesting phenomenon that happens across a large number of different types of materials, paper, glass, all sorts of things. And the idea here is explained pretty well in this Nature paper from '98, and that's what this figure is from. And essentially, they attribute this to a thermally activated process that's occurring over a really large distribution of gap distances between asperities in the contacting region. Each one of those gap distances has a characteristic time for formation of a capillary bridge, and then you end up having essentially usually a logarithmic dependence of the spring constant and friction coefficient with time. Reference 7 there is interesting too if you have a chance to look at it. This is actually talks about a QCM experiment very similar to what I've just showed. So how can we probe this aging thing in greater detail? So what I did was make use of a QCM flow cell that I built years ago to try to study self-assembled monolayers and things, liquid processes like the growth of cadmium sulfide and other aqueous chemically grown films that we use in our laboratory. So I've adapted this apparatus to gas flow rather than liquids as depicted here in the schematic on the left. And what we're able to do is to put the QCM into a little flow cell. So this is a very small volume, 1/10 of a milliliter flow cell, and have a computer toggle gas flows. In this case, it's water saturated nitrogen and dry nitrogen over the surface of this crystal with glass spheres on it. This figure on the right shows the output of a couple different runs. That black trace is the one that I just showed you, where we have just simple glass spheres with no humidity cycling going on. The gray trace is with humidity cycling, and if you zoom up on that data, the trace is actually very wide because there's a bunch of humidity and drying cycles here. So this is actually the spike here is from adsorption of water. These the low points here are as dry nitrogen goes across the spheres, and this repeats every couple minutes. And I have been doing these experiments overnight. So you can see immediately that the humidity cycling drastically changes the rate at which the friction coefficient between these glass spheres and the SiO2 coated resonator changes with time. The yellow trace again here is another control, just showing this one with this control is done with humidity cycling also. So you see immediately that the width of this trace is larger simply because there's more surface area here on the in the case where we have glass spheres on the crystal as well. The idea
let's have this as your last slide, okay?
Pardon?
Let's have this as your last slide. Is
Okay.
that okay?
Sure.
Maybe wrap it up with a final remark.
Sure. Well, I'll just say quickly that I didn't realize I was out of time. Anyways, we can do this with other particles other than glass spheres. That's not really the problem with soiling. but we can detect the onset of cementation, and in this case we show an opposite trend. We have a decrease of the frequency. This means we've essentially been able to detect the transition from sliding contact to rigidly adhered particles. Since these are going to be available online, I can just let you quickly look at the pros and cons of this type of experiment. I think there's probably a better way to do that. This is there's a couple papers that I became aware of at an APS meeting in November in Nashville. This is really interesting work from Michael Gruns' group. But I just wanted to say that ultimately, future work, we need to include this kind of shear force assays that Michael Gruns has done. I believe the QCM stuff is very interesting, but we have to develop some simpler field tests, and it's relatively straightforward to do temperature and humidity dependent studies with this. Ultimately, we need to be able to recommend best practices for module cleaning and identify different soil types that are most prone to cementation and help develop these soiling resistant coatings.
Thank you, Craig. The chat here has a number of good questions that we'll get back to, but this is a talk that's generated a lot of interest. Let's go to our next speaker. Clemens, are you ready to take control and start your presentation?